In this video, we're going to draw the loose star structures and predict the geometries of some compounds that have actually multiple central atoms. So let's take an example of CH3CHO. So in this case, both of those carbons are going to be acting as the central atom. So let's start out with calculating getting the total valence electrons. So the number of valence electrons in this particular compound, we have 2 carbons, so that's going to be 4 times 2 because each carbon has 4 valence electrons, and then we have 4 hydrogens, so each hydrogen is going to have 1 valence electron, so 4 times 1, and then plus we have 1 oxygen, and 1 oxygen is going to have 6 valence electrons. So that adds up to a total of 18 valence electrons. You want to make sure you use up all 18 valence electrons. Now, since I said there's 2 central atoms and both of those carbons going to be the central atom, so go ahead and connect those 2 carbons with one another first with the help of a bond, and then see what's going on with the left carbon and what we have on the right carbon. So we can clearly see on the left carbon we have 3 hydrogens. So I want to have those 3 hydrogens as surrounding atoms and connect those with one bond. Okay, and then on the right carbon we have 1 hydrogen and 1 oxygen. So you want to connect all those surrounding atoms with the central atom by 1 bond right now. So then once you do so, you want to count how many electrons you used, and since there are actually 6 bonds total, and 6 bonds going to bring in, will use up 12 electrons, so you want to subtract 12 from 18, and that gives you a remaining of 6 electrons that needs to be used now. Now you want to make sure you complete the octets of the surrounding atoms, and hydrogen needs only 1 bond, so all the hydrogens are happy as it is. But then when we look at oxygen, oxygen right now has only 1 bond, and since it has only 1 bond, it would need 6 more electrons to complete the octet. So that's the typical rule we use. We want to complete the octets of the surrounding atoms before we look at anything else. Now, before we actually finalize our structure, you want to make sure everyone is happy in terms of the octet. Looks like this carbon, the first carbon is fine. Okay, so this first carbon is fine because it's got 4 bonds around it, so that means it has 8 electrons on it. What about the second carbon here? The second carbon that's on the right side has only 3 bonds around. That means it's got only 6 electrons so far. So what you have to do, you want to make sure you create a double bond here. All right. So before you finalize your structure, you must make sure everyone is happy with their octets. So you want to go ahead and create the double bond there. So your final structure would actually look like this. So you have the left carbon with 3 hydrogens, and then it's connected with the second carbon, and the second carbon is going to have double bonded oxygen and then 1 hydrogen. So now everyone is happy. Both of those carbons has 4 bonds, which means they both have 8 electrons each. Oxygen has 8 electrons, and all the hydrogens have 2 electrons. That's what they really need. So that's going to be your finalized structure in this particular case. But then the question is, what's going to be the geometry on those? So if I look at this carbon right there, we have 4 electron domains. All right, since we have 4 electron domains around that carbon, it's going to be in a tetrahedral structure. There's no lone pair, so that means your electronic geometry and the actual shape is going to be the same, and that's going to be a tetrahedral in this case. And obviously you want to know the electron geometry, but your shape is more important, and that's going to be tetrahedral for this particular case. And then what about the second carbon? The second carbon, how many electron domains do we have? Well, we got only 3 bonds around. This double bond still counts as 1 electron domain. Even if you have a triple bond, it's going to count as a 1 electron domain. So it's got 3 electron domains, and since it has 3 electron domains, what's going to be the shape in electron geometry? Since there's no lone pair on the central atom, well, it's going to be a trigonal planar. Okay, so that's what you really have to look for. And what about the polarity of this molecule? Just to kind of look at what's going on with the polar and nonpolar. Well, what we have learned that if you have a bond that's between the same atom, that's going to be nonpolar. So this carbon-carbon bond is nonpolar. What about this carbon-hydrogen bond? Is that considered nonpolar or polar? Well, even though carbon is a little bit more electronegative than hydrogen, there's not a big difference in the electronegativity. So this is still going to be a nonpolar bond. Okay, is there any bond in this molecule that's going to be polar? Well, let's focus on this oxygen and carbon. Who is more electronegative between oxygen and carbon? Well, oxygen is going to be a little bit more electronegative, so as a result, it's going to have a partial negative charge. So we'll have a partial negative charge on the oxygen, and we're going to have a partial positive charge on this carbon as a result. So there is a net dipole going uh, from this carbon to the oxygen in this direction. So since there is a net dipole in this molecule, this we're going to call that a polar overall. So net dipole in the molecule, so it's going to be polar overall. Okay, so that's how you determine. There are going to be times when you have one side of the molecule to be nonpolar, but the other side to be polar. So like if I look at this side of the molecule, you can say it's actually nonpolar, which is completely okay, but then the right side of the molecules is polar. So since it's a small molecule, you can say the overall molecule is to be polar. So this side is going to be nonpolar. Okay, all right, so that's how you're going to be drawing the Lewis-Dot structures of a compound that has multiple central atoms. Let's take another example. What if I have C2H4 Cl2. Okay, so in this particular case, we're not really told how the connection is going to be. You just have to figure out what's the best way of connecting all those carbons and other surrounding atoms. So in this case, when we look at, okay, hydrogen is not going to be the central atom, chlorine is not going to be the central atom because it's more electronegative than carbon. So as we have said earlier, if you see in a carbon, that's going to be most likely your central atom. And consider both of those carbons to be the central atom. So you have two central atoms in this case. So let's first figure out the total valence electrons. So we have two carbons, that's going to be 2 times 4. And then we have 4 hydrogen, so it's just going to be 4 times 1. And then we got plus 2 chlorine, so that's going to be 2 times 7. Each chlorine has 7 valence electrons, so make sure you get the valence electrons correctly. So that's going to be 8 plus 4, 12 plus 14, and that's going to be 26 total electrons in this particular compound. Okay, so then I would go ahead and connect this carbon with this carbon because both of those are going to be the central atom, and central atoms must be connected with one another. So then I don't know really the distribution between like which carbon gets how many hydrogens or how many chlorines. So there is multiple possibilities on those compounds. Like since you're not told, you can have multiple isomers on those. So let's assume I do this. I have one first carbon gets the 3 hydrogen, and it's just like I'm putting multiple possibilities there. So when you put the first hydrogen, 3 hydrogen on the first carbon, that uses up all 4 bonds there. And then the second carbon will have 2 hydrogens, 1 hydrogen rather, because you already have 3 hydrogens taken away. And then the other 2 atoms going to be the chlorine. So you're going to have a chlorine here and a chlorine here. Okay, so that's one possibility of drawing it. And then you want to go ahead and calculate how many electrons you use. So far you have 7 bonds in there, so that means you used 14 electrons. So then you subtract those, that leaves you with 12 electrons remaining. So once you have 12 electrons remaining, you want to make sure the octets are completed for every single atom there. And hydrogens are happy. What about those carbons? Well, each carbon has 4 bonds around it, and from the previous lectures, we have learned that carbon wants to have 4 bonds so that it can have a total of 8 electrons. And then what about the chlorines? Well, chlorines does not have the octet completed. Right now, each of the chlorine has only 1 bond, so we want to go ahead and put in 3 lone pairs on each of the chlorine. And that uses up the remaining 12 electrons. So now you have all the electrons to be used there. Okay, so then that's one possibility. what about looking at the geometries of those? So let's assume this carbon here, and a matter of fact, both of those carbons has actually how many electron domains? They both have 4 electron domains total. And since they don't have any lone pairs on the central atom, their geometries and their electronic geometry is going to be the same. So that's going to be tetrahedral. Okay, well that was actually one possibility where the chlorines could be only on one carbon. What if you, like, since we're not told where the chlorine's going to be and where the hydrogen's going to be among those two carbon atoms, the other possibility could have been, what if I have one chlorine on one carbon and the other chlorine on the other carbon, and then distribute the rest of those to make up the remaining 4 hydrogens there. So that's the other possibility. And just go ahead and calculate your valence electrons and all that, and then it's going to come out to be 3 lone pairs on each of those chlorine to make up their octets. So that's another possibility. And in this particular case, both of these compounds actually have the same formula. All right, so since they both have the same formula, however, their structures are different. Like in one compound, the one carbon has 2 chlorines, and in the other compound, each carbon has 1 chlorine. Okay, so when you have the same formula, so in this case you have same formula, but different structures, they're called isomers. So this particular one, there are different types of isomers. For right now, you just want to know if you have the same formula, but different structures, they're going to be called an isomer. And later on, you guys are going to be learning on different types of isomers. So this is how you're going to be drawing multiple centers compounds. I can take another example quickly, and I'll probably just do this quick. Let's say I have uh, C2H4. Okay, so C2H4, and if I count the total valence electrons here, and I'll probably just do that quickly. So I got 8 from the carbons and 4 from the hydrogen, so that's a total of 12 valence electrons. Both of those carbons are going to be the central atom, so you want to connect both of those carbons as with a single bond first, and then um, what possibilities you can have? I mean, you have to kind of uh, draw maybe multiple possibilities and see which one fits the best. What if I put, for right now, if I put maybe 3 hydrogens on one carbon and 1 hydrogen on the other carbon and see if it really fits it? And if it doesn't fit it, then you're going to have to try something else, all right? So then assume how many electrons we used here. So we have 5 bonds around. We used 10 electrons, all right? So that means you still have 2 electrons remaining. Now those 2 electrons could go, will not go to any of those hydrogens because they're all happy. But I can go ahead and put it on this carbon right there, and it seems like that doesn't really help us because this carbon is still not going to have an octet completed. So this structure is not going to be a good one. So then you're going to try something else, and when you try something else, what about having 2 hydrogens on each of those carbons? Okay, so that's another possibility you can have. Either you can have 3 hydrogens on one carbon and 1 hydrogen on the other carbon, or you can have 2 hydrogens on each of those carbons and see how that plays out. So then when you count all those electrons, you're still going to have 2 electrons remaining out of the total valence electrons. So that means I can have that 1 lone pair on one of the carbon atoms. And still right now, I can kind of see the left atom, the right carbon has the octet completed, but this left carbon does not have the octet completed. So to make everyone happy, I could go ahead and create a double bond there. So that means this lone pair is going to be used to create a double bond between those 2 carbon atoms. So that's how the structure of this C2H4 going to look like. Obviously, I could not do that in the previous setup, like in this first setup where we have a lone pair on this carbon. Even if I go ahead and put this on here to create a double bond, there's two problems. This carbon, the first carbon will still not have the octet completed, and the second carbon will have more than 4 bonds. And carbon does not want to have more than 4 bonds. After on the fifth bond, it's going to have 10 electrons, and carbon does not have 10 electrons. It does not violate the octet rule. So this is the final Lewis dot structure is going to be for this particular one. And when you count the electron domains on both of those, it's 3 electron domains. And since you have 3 electron domains and there's no lone pair on those carbon atoms, the geometry and the electron geometry shape is going to be trigonal planar. All right, so hopefully this was helpful when you're drawing the compounds Lewis dot structure that has multiple essential atoms. And if you have any questions, leave the comments below.